and transmittance. Now we may have to relate these three different terms using conservation of energy. Using conservation of energy, total amount of energy falling on that particular object will equals to amount of energy absorbed, reflected, and transmitted. Now move this Qi to right side, or just divide this entire term by Qi. So Qi divided by Qi, A plus Qt divided by Qi. Qi and Qi will cancel out, so you're left with just 1 equals to Qa divided by Qi is absorptivity or absorptive power A. Q reflected to the total radiation falling on it is a reflectance, and Q transmitted to the total radiation falling on it is termed as reflectance. So in general, sum of these three different terms will equals to unity. Hamza, is it clear?
Yes, sir.
Now for this part, let's say for vacuum, there will be no possibility of absorption for vacuum, and so there is no reflectance for this particular vacuum. So complete transmittance, that will be 1. So you'll be asked to define a material or a medium which having perfect transmitter or 100% transmittance. So it will be vacuum. So it will be termed as perfect transmitter of radiation. Next is for mirror. There will be no transmittance. So A plus R equals to 1. And for mirror, there is more possibility of reflecting, or there will be more tendency of reflecting that particular radiation as compared to its absorbing tendency. So from this part, since sum of these two quantity will always equals to 1, so there will be more reflectivity or reflectance, so it will have lesser absorbing tendency. So we can say good reflector are bad absorber, and vice versa. Hiba, is it clear?
Yes, sir.
Now, next is for black body. It is a body which having tendency to absorb all radiation falling on it. So transmittance will be 0, and there will be also no reflectance. So absorbance will become 1. So it will behave as perfectly absorber. So we may define this black body as a body having tendency to absorb all radiation falling on it. Khalid, any doubt?
No, sir.
Okay, just write it down. You all have written?
Yes, sir.
Now, for this black body, we may define two more terms. First is emissive power. So it is amount of energy emitted by any object per unit area per unit time. So it is the amount of energy emitted by a body per unit area per unit time. So emissive power is equals to energy radiated by a body per unit area per unit time. This particular quantity is also equals to intensity. Next is emissivity, denoted by epsilon or sometimes small e. It simply relates the emissive power of any ordinary body to the emissive power of perfectly black body. So it is just a ratio of emissive power of ordinary body to the emissive power of black body. So epsilon equals to emissive power of ordinary body divided by emissive power of black body. So in general, all ordinary body will have lesser emissivity as compared to, or lesser emissive power as compared to black body. So epsilon will lie from 0 to 1. Only in case of black body, epsilon will equals to 1. Hamza, is it clear?
Yes, sir.
Okay, just write it down. Hiba, done?
Yes, sir, done.
Okay. Now, related to these different terms, let me define you about Kirchoff's law of radiation. It simply states the ratio of emissive power and absorptive power of any ordinary body will equals to emissive power of perfectly black body at that given temperature. Or simply in other sense, you will say emissive power of a particular body will be directly proportional to its absorptive power. So the more it will have tendency to absorb radiation, the more it will have tendency to emit that. It means good emitter must be good absorber first. Hamza, is it clear?
Yes, sir.
So Kirchhoff's law of radiation is the ratio of emissive power and absorptive power of any ordinary body at fixed temperature or at given temperature is equals to emissive power of black body at that temperature. It means emissive power and absorptive power of any ordinary body must equals to emissive power of black body at that temperature. Hiba, any doubt?
No, sir, no doubt.
Okay, let me prove this particular statement, then I'm defining its consequence part. Suppose you have any ordinary body, let's say this. Any ordinary body and perfectly black body. Suppose same amount of radiation fall on this and on this. So according to tendency of absorbance, we may define A equals to Q absorbed divided by Q incident on it. So Q absorbed will equals to A times Q incident related to this particular ordinary body. But in case of black body, where absorbance or absorptive power will be just 1, so 1 equals to Q absorbed divided by Q incident. So Q absorbed will equals to Q incident. Hamza, is it clear? Since for black body, absorptive power will be 1, that's why Q absorbed will be Q incident. It means it will have tendency to absorb all radiation falling on it. There will be no reflectance, no transmittance. Is it clear?
Yes, sir.
Now, according to the formula, epsilon is emissive power of any ordinary body divided by emissive power of black body. This particular ratio is also equals to their absorptive power as well. So it will be equals to absorptive power of ordinary body divided by absorptive power of black body. Now, if you put the above values in this expression, you will get emissive power of ordinary body divided by emissive power of black body equals to absorptive power of any ordinary body is A times Q incident divided by absorptive power of black body at that temperature is Q incident. So this and this will cancel out. So if you move this A towards denominator and this denominator towards right side, you will get emissive power of any ordinary body divided by A, which is nothing but absorptive power of ordinary body. And right hand side for this particular denominator, it will be equals to emissive power of black body. This was Kirchoff's law of radiation. Is it clear?
Yes, sir.
Solid?
Yes, sir. Clear.
Okay. Just write it down. You all have written?
Yes, sir.
Salman?
Yes, sir, done.
Okay. Now, from this part, we may write, if you move this denominator to right side, so you will get emissive power of any ordinary body equals to emissive power of black body multiplied by absorptive power of any ordinary body. I've just moved this denominator to right side. Now, in this expression, this particular quantity, emissive power of any ordinary body, is directly proportional to absorptive power of that particular ordinary body, since emissive power of perfectly black body will be constant. So from this part, we can say the more the tendency of absorbing of a particular body, then it will have tendency to emit more, or good absorber will be good emitter. So good absorber will be good emitter, but bad reflector. Iba, is it clear?
Yes, sir.
Okay, just write it down. I'm giving you question related to this part. You'll have done? Hamza, done?
Yes, sir, done.
Okay. Now, in a particular, let's say, jar or a particular pan, I've taken 3 different colored dye, blue colored, black colored, and red colored, which are directly exposed to radiation for some time. Now, they have shifted in any dark room. So, which color do you think will glow most? Khalid, any
Yes, sir.
idea?
Sir, maybe red.
A red one. Okay. Hiba, blue one or black one or red one?
So maybe black one.
Okay. Hamza,
The black one.
why?
So because it is a good absorber, so a good
Good,
absorber will be good emitter.
good. Since the more the tendency of a particular body to absorb, so in all color, black will having tendency of maximum absorbing, and hence it will also have more emitting tendency. So black will glow most than the other color according to Vibcure. I will define you about Stefan's law later, on the basis of which you may define these terms. So up to this part, black having tendency to absorb more, so it will further radiate more. Khalid, is it clear?
Yes, sir.
So you can say, since black dye will have maximum absorbing tendency, hence it will also emit more Okay, just write it down. Hamza, done?
Yes, sir, done.
Okay, these are some theoretical concept of this particular radiation. Now we have to calculate related to this part, numerical term, how much it has tendency to radiate or how much radiation it will emit at a particular temperature. Just 1 minute. Okay, so according to this part, we may define first Stefan's law. According to Provost's hypothesis, which state every body which having temperature greater than 0 Kelvin will emit and absorb radiation at all time. But how much radiation it will emit or absorb, it will be defined by Stefan's law. Is it clear?
Yes, sir.
Yes,
So
sir.
Stefan's law simply says emissive power of any black body will be directly proportional to fourth power of their absolute temperature. So more the temperature of a particular body, it will have tendency to emit more, or it will have more emissive power. So emissive power is also equals to energy radiated per unit area per unit time equals to, if you replace this particular proportionality sign, there will be a constant of proportionality sigma, temperature to the power 4. This sigma is called Stefan's constant, and it is equals to 5.67 into 10 raised to minus 8 watt per meter square Kelvin to the power 4. This particular quantity is also equals to intensity. So we may define this as Stefan's law as the amount of radiation emitted by a black body per unit area per unit time is directly proportional to the fourth power of their absolute temperature. Khalid, any doubt?
No, sir.
Okay, just write it down. Hamza, done?
Yes, sir. Done.
Okay. This is for black body, but if you have to define for any ordinary body, so emissivity equals to emissive power of any ordinary body divided by emissive power of black body. So from this part, we may write emissive power of ordinary body equals to epsilon times emissive power of black body, and it is equals to sigma times T to the power 4. Now this emissive power is also called energy emitted or radiated by any ordinary body per unit area per unit time. This is also called intensity. Energy per unit time is also called power, so may be written as power divided by area, and should be equals to epsilon times sigma t to the power 4. So this is for any ordinary body, in which we may define epsilon for different object. Is it clear?
Yes, sir.
Okay. Just write it down. Iba, done?
So the last part.
Okay.
Done, sir.
Okay. Now, related to this concept, you will be asked first, if two black body at 1 to 7 degrees Celsius and 7 to 7 degrees Celsius, find ratio of their emissive power. If ratio of their radius is 2:1, find ratio of power emitted. Just use the above formula. First, try to convert temperature into Kelvin and then simplify it. Since we have to calculate for black body, so epsilon will equals to 1. So in first part, for emissive power or simply intensity equals to sigma times t to the power 4. So epsilon 1, intensity 2 will equals to sigma t to the power 4. So T1 over T2. In case of power, P1 divided by P2 equals to area times intensity. So it will be sigma A t to the power 4 1 1 divided by sigma A t to the power 4. Just put their values and simplify it. Hamza, any problem?
No, sir.
You got answer for first part?
Yes, sir.
Just send me. Hiba, just send your answer. Khalid,
Yes, sir.
just send your answer.
Okay.
Hamza, just tell me the value of T1.
500 Kelvin.
What you got for T1 in Kelvin?
Sir, 500.
Okay, 500 Kelvin. And T2,
1000.
1000 Kelvin. So according to this formula for intensity, I1 over I2, sigma and sigma will cancel out. Okay,
Yes, sir.
so you're left with T1 over T2. And how much exponential?
Sir,
4.
4.
Okay, so T1 is 500 Kelvin and T2 we have 1000 Kelvin raised to power 4. So this 500 will cancel out this 1000 in 2 times. And this 1 over 2 get multiplied to 4 times. So it will become 1 over 16. Is it clear, Hamza?
Yes, sir.
So how you got this answer?
Sir, I forgot the exponential power.
Okay. Similarly, for power, P1 over P2, sigma and sigma will cancel out. So area, that is surface area of that body. So all objects tend to be spherical in shape. So area will be 4 pi r squared times T1 to the power 4, 4 pi r squared and T2 to the power 4. So 4 pi cancel out. So R1 over R2 square times T1 over T2 power 4. R1 over R2 we have 2 divided by 1 square, and T1 over T2 we have 1 by 2 to the power 4. So 2 divided by 1 on squaring will become 4 by 1, and 1 by 2 on taking 4 power, it will be 1 by 16. So 4 in 4 time, so it will become 1 by 4. Hiba, you got the same answer or something else? Khalid, is
The
it clear?
first one I got the same answer.
Okay, good. Hamza, done?
Yes, sir.
Okay. This is all about when object is placed in vacuum, where is there no interaction with surrounding. But let's say if body is kept in any cold surrounding, so what will happen at that particular case, which is defined by Newton's law of cooling. Let's say there is a body at absolute temperature T is placed in any cold surrounding, having temperature T naught. Temperature of this particular body, T. So according to proposed hypothesis, says every object having temperature greater than 0 Kelvin will emit and absorb radiation at all time. So this hot body having more temperature, so it will radiate more along this way. And since it is placed in cold surrounding, so that cold surrounding also radiate energy along this way like this. So there will be some net flow of radiation in between these two interacting bodies. Consider a hot body at temperature T is placed in cold surrounding. Of temperature T naught. So there will be some outward radiation and there will be some inward radiation. Outward radiation per unit area per unit time equals to sigma times T to the power 4 into epsilon, since it is not a perfectly black body. Similarly, inward radiation to that object divide by area into time will be equals to epsilon sigma T naught to the power 4. So net flow of radiation will be outward of this particular object, since object having larger temperature as compared to its surrounding. So net flow of radiation per unit time and per unit area will equals to epsilon sigma and difference of this particular two different quantity. Khalid, is it clear?
Yes, sir.
Okay, just write it down. This is not Newton's law of cooling. I will define you later, but this is the hypothesis from which Newton's law of cooling is derived. Hiba, done?
Yes, sir, done.
Okay. Now, related to this net flow of radiation, it will causes to loss of heat. So you may write this particular net flow of radiation as heat lost per unit time. Move this area to right side, epsilon A sigma. And for this particular temperature, let's say delta T equals to T minus T naught. I'm taking this delta T to be less than equal to 100 degrees Celsius. So in place of T, we may write delta T plus T naught. So if you put this particular term in this expression, you will get T naught plus delta T in first part to the power 4 minus T naught to the power 4. Khalid, is it clear?
Yes, sir.
Next is we have to simplify this particular segment. Epsilon A sigma being constant. If you have to take out T naught from this fraction, so just multiply it and divide this particular part. So if T naught taken out as common, so it will become T naught to the power 4, 1 plus delta T divided by T naught to the power 4 minus of T naught to the power 4. Iba, is it clear?
Yes, sir.
Okay. According to Bernard, further, T naught and T naught get common from both these two segments. So you'll get epsilon A sigma T naught to the power 4 being common. So you're left with 1 plus delta T divided by T naught to the power 4 minus 1. According to binomial expansion, if 1 plus x raised to n, it will become 1 plus n times x. It means the exponential get multiplied with the coefficient of x if x is very, very small as compared to 1. So using this, we may write this above expression as heat loss per unit time dq over dt equals to epsilon A sigma T naught to the power 4, 1 plus this 4 get multiplied with this part delta T over T naught minus 1. This one and this one will cancel out. So on simplifying, epsilon A sigma T naught to the power 4 multiplied by this delta T, which was T minus T naught, divided by T naught. So on simplifying, you will get 4 epsilon A sigma T naught to the power q and T minus T naught equals to dq by dt. Khalid, is it clear?
Yes, sir.
Okay, just write it down. Hamza, done?
Yes, sir. Done.
Okay, so from last part, we may define this dq by dt equals to this quantity with some constant part So dq by dt simply defines you heat lost by that particular object per unit time. This particular term is constant, so it mainly depends upon temperature difference of body and surrounding. This is called Newton's law of cooling. So we may write when a hot body is placed in cold surrounding, the rate of heat lost by body is directly proportional to the temperature difference of body and surrounding. Hiba, is it clear?
Yes, sir.
So don't prove the above part. I've just proved to define or to show you how we got this particular result. But if you have to prove this particular part for your examination, so you may write from this part. Okay. So according to this, rate of heat lost by body is proportional to temperature difference of body and surrounding. So rate of heat lost by the body is dq over dt. Since heat is being lost, so there will be some negative sign equals to proportionality constant C T minus T naught. C will be equals to 4 epsilon A sigma T naught to the power 3, what we have derived above. Now, this particular loss in heat of that particular object will cause us to change its temperature. So we can say this loss in heat will cause to change in temperature. So the heat which is responsible to change the temperature of a particular object is called specific heat. So we may write dq equals to mass specific heat times change in temperature. So on putting the above part, it will be equals to ms dt divided by dt equals to minus of c times t minus t naught. So on moving the constant part to right side, you may write dt divided by dt equals to minus c divided by m into s, another constant, times t minus t naught. Khalid, is it clear?
Yes, sir.
Hamza, any doubt?
No, sir. No doubt.
Okay, just write it down.
Sir, could you show the final equation again?
Salman, done?
Yes, sir. Done.
Okay. Now, related to this last expression, we have to define temperature with respect to time. So move this T minus T naught to the right side. I will use this expression later to calculate shortcut formula. Now, we may write dt divided by T minus T naught equals to this particular term to be another constant. So let's say K with negative sign times dt integration. Let's say at time t equals to 0, this part will have some initial temperature Ti, and sometime t, it will have some temperature final. So if you integrate this particular part, which is similar to dx by x, so on integration, you will get ln or natural log t final t initial equals to minus of k and dt on integration t having value 0 to some t. So if you solve this particular part, you will get expression like ln t final minus t naught minus, which will be, I've just moved it to right side. So you'll get plus ln t initial minus t naught. So which is quite similar as y equals to mx plus c. Is it clear?
Yes, sir.
So you'll be asked, what would be the nature of graph related to this part? Since it is behaving as a straight line, so graph will be straight line with negative slope and positive intercept. So this is log of temperature minus T naught. So it will go from this point, that is from initial temperature, along a straight path like this to cool down in some time t. So if you take a horizontal line to define its slope, slope will equals to k, which is equals to c by m into s, or c having 4 pi or 4 epsilon sigma t naught to the power 3 multiplied by a divided by m into s. It means greater the value of specific heat of that substance, it will have smaller slope, and vice versa. Hamza, is it clear?
Yes, sir.
But if you resolve this particular part, log part, in terms of exponential, you will get another expression. So if you remove this ln part, so you will get T final equals to some exponential function minus of k into t plus some constant part which is also in terms of exponential function as well. So graph related to this expression will look like t versus t will be exponentially decreasing like this. So you'll be given to draw graph for ln part or simply normal temperature part. So in case of ln, it will be a straight line with negative slope. In case of normal temperature, it will be exponentially decreasing like this. Khalid, is it clear?
Yes, sir.
Okay, just write it down. Hiba, done?
Yes, sir, done.
Okay. But for calculation part, since log or calculation of log will be quite difficult, so let me define you shortcut method to solve problem related to this part. As we have in above, dt divided by dt equals to minus of some constant k, t minus t naught. So this dt is also called change in temperature. So it will be T final minus T initial divided by change in time T minus 0 equals to minus K. T, it will have average temperature Ti minus T naught divided by 2 minus T naught temperature of surrounding. Now since TF will be always smaller as compared to Ti, so if you reverse this particular fraction, you'll get negative sign. And this negative and this K negative will get cancelled out. So you're left with Ti minus Tf divided by time taken equals to K Ti plus Tf divided by 2 average temperature minus temperature of surrounding. So this will be our final expression of Newton's law of cooling, for which or on the basis of which you will be able to calculate different problems. Hiba, done?
Yes, sir, done.
Okay. There will be question like a body at 60 degrees Celsius is placed in surrounding of 10 degrees Celsius, cools down to 40 degrees Celsius in 5 minutes. Find time to cool it down further to 20 degrees Celsius. So for this problem, we have two segments. First, object was initially 60 degrees Celsius, cools down to 40 degrees Celsius in first 5 minutes. So in how much time it further cooled down to 20 degrees Celsius? We have to calculate it. Time taken for this duration is 5 minutes, and time duration for this, we have to calculate it. Temperature of surrounding is fixed, T0, as 10 degrees Celsius. So for each segment, just in first part, we have T initial as 60 degrees Celsius and T final as 40 degrees Celsius. Time taken for this particular loss in temperature is 5 minutes. So 5 into 60, it will be 300 seconds. Similarly, in the second half, from this point to this point, we have T initial as 40 degrees Celsius, T final as 20 degrees Celsius, and time we have to calculate it. So write the above equation, put their values, and try to find K from the first expression, put it in the second part, and try to find time for the second process. Is it clear?
Yes, sir.
Try to solve, everyone, please. Hiba, any problem while solving? Khalid, you got any answer?
Yes, sir. I'm still calculating.
Okay. Okay, just see. According to the formula, Ti minus Tf divided by time taken equals to K Ti plus Tf divided by 2 minus temperature of surrounding T naught. So for first part, if you put the values, so it will be 60 minus 40 divided by time taken 300 equals to K Ti 60 plus Tf 40 divided by 2, temperature of surrounding 10. So on solving, 20 divided by 300, K 60 plus 40, 100 divided by 2, 50 minus 10. So it will be 40. So 20 in 2 times become 40. So K will equals to 1 by 600. Hamza, is it clear?
Yes, sir.
Now for second part, we have T initial 40, T final 20 divided by time taken. We have to calculate K, which is 1 over 600, times Ti plus Tf 40 plus 20 divided by 2 minus temperature of surround. So 40 minus 20 will be 20 divided by T, 1 by 600, 40 plus 20, 60 divided by 2, 30 minus 10. So it will be 20. This part will cancel out. So you'll get T is equals to 600 second, or simply T is equals to 600 by 60. That will be 10 minutes. Khalid, is it clear?
Yes, sir.
Was there any so tough calculation in this entire part? I think so. No. Okay. Just write down.
Sir, no tough calculations in that.
Yes, Salman.
Sir, I told there's no tough calculations.
Okay. Hiba, done?
Yes, sir, done.
Okay. Now let me define you a concept related to this question. We had initially temperature of body at 60 degrees Celsius, then converted to 40 degrees Celsius, and then reached to 20 degrees Celsius. In both process, from this point to this point, and from this point to this point, how much is the temperature difference? Hamza?
Sir, 40.
For first part,
Oh, okay.
60 to
First part,
20,
it is from 60 to 20.
60 to 40, 20 degrees Celsius. And then again, in second part, from 40 to 20, it's just 20 degrees Celsius. Is it clear?
Yes, sir. I thought you asked for the whole.
Okay. So in first part, time taken to go from 60 degrees Celsius to 40 degrees Celsius was 5 minutes. But in second part, we have calculated it is taking 10 minutes. Is it clear?
Yes, sir.
So from this part, we may conclude at low temperature, suppose initially body or the temperature of this particular object was 60 degrees Celsius. So temperature of this particular body subtracted to the temperature of surrounding, you will get 50. But for this part, 40 minus 10, it will be 30. So at low temperature, it will take longer time to change by same amount of temperature as compared to higher temperature. Initially, it was taking just 5 minutes to go from this point to this point. But now in this part, it is taking 10 minutes to go from this point to this point. So if you have to calculate same amount of temperature, so at higher temperature, it will take smaller time, but at low temperature, it will take longer time. Is it clear?
Yes, sir.
So we can say from this part, as temperature of object decreases, its rate of cooling or its rate of heat lost by the body also decreases. So to change by temperature, same amount, it will take longer time at lower temperature as compared to higher one. Khalid, is it clear? So from this part, we can say as temperature of body decreases, T minus T naught also decreases. So rate of cooling or heat loss will also decreases. Hence, it would take longer time to change temperature by same amount at lower temperature. Hiba, is it clear?
Yes, sir.
Now, related to this concept, there will be a question. Suppose you have a body initially at 90 degrees Celsius, cools down to 80 degrees Celsius, further to the 70 degrees Celsius, and further to 60 degrees Celsius. Time taken in first part is T1, second part in T2, and third part is T3. So how T1, T2, and T3 will be related? How T1, T2, and T3 will be related? Will all they be equal, or there will be some other relation? Hamza, just try to relate the above expression to this part. Just write it down. Khalid, just tell me the relationship between these three different times.
Sir, I think T3 will be the longest.
Okay. And T1 will be the least.
Yes, sir.
Okay. Hiba, is it the same, or it will be something different?
Sir, same.
Good. Since in this part we have also same temperature difference, 90 to 80, 80 to 70, and 70 to 60. But as the temperature of body decreases, it will take longer time to change by same amount, since the rate of cooling of that particular object decreases. Hence, T1 will be least, then T2, and then T3. Salman, is it clear?
Yes, sir, it's clear.
Okay. Now, the last part of this particular chapter is Wien's displacement law. Suppose you have any ordinary body, let's say any rod, which is placed over any flame like this. So which color do you think it will start radiating first? Green, blue, red, yellow? Hamza?
Sir, red.
Okay. If you further increase its temperature, then
No, okay. Red will be later. I guess first it will be blue.
Initially, it would be blue, then it will changes into red later on.
Yes, sir.
Okay. Khalid, would you like to change? Or you'll go with this?
Sorry, sir, could you repeat the question?
If you place this particular rod on a particular fire, so in which color this particular rod will start radiating initially, and how will color will transform on increasing temperature?
Sir, it will change into red color
Initially or after on?
after, like reddish orange color.
So initially it will start glowing in red color, then it changes into reddish orange and
Yeah.
further.
Yes.
Okay. Let me define you the concept behind it. Every object which having temperature T, so it will have some thermal energy that will be about 3/2 times kBT. And due to this thermal energy, it will start radiating radiation. So you may call it will radiate or emit photon having energy at C by lambda. Now just compare these two segments. We have rest of whole term constant, just T is variable and this lambda is variable. H is Planck's constant, C is speed of light. So these are constant. So from this part, we can say for higher temperature, it will have more thermal energy. And in terms of wavelength, the smaller the wavelength of radiation, it will have more energy. So if you combine these two expressions, you will say at low temperature, it will radiate longer wavelength, and on increasing temperature, wavelength must decreases. So it will start radiating smaller wavelength. So you must have learned about Vibgyor, radiation in visible region. So in this spectrum, wavelength is least wave, violet having least wavelength, and red having maximum wavelength. So according to this concept, at low temperature, it will radiate longer wavelength. That's why initially color of the rod will be red. On increasing temperature, wavelength decreases, so it may get shifted towards orange, yellow, and so on. Hamza, is it clear?
Yes, sir.
So from this part, we can say the wavelength of radiation emitted by a hot body is inversely proportional to their absolute temperature. It means let's say this is first radiation, which having temperature this and wavelength this. Similarly, if you change the temperature, it will radiate some different wavelength like this. So wavelength increases and temperature decreases. This is wavelength versus temperature. So it will be T1, T2 corresponding lambda 1, lambda 2. So from this part, we can say lambda maximum inversely proportional to absolute temperature. So if we move this temperature to left side, lambda maximum into T equals to some constant, which is equals to B, which is equals to 2.29 into 10 to the power minus 3 meter Kelvin, or you may write 2.3 into 10 power minus 3 meter Kelvin. This is equals to, or this is called Wien's displacement constant. Iba, in it out?
No, sir.
Okay. Just write it down. You all have done?
Yes, sir, done.
Salman, any doubt?
No, sir, no doubt for now.
Okay. So this is the entire part of this thermal properties of matter. So we have just completed. So from next class, we'll start with thermodynamics. Okay. So just revise this entire part and try to do assignment. Okay.
Okay, sir.
Yes, sir.
Okay then. Take care. Allah Hafiz.
Thank you, sir. Allah Hafiz.